So the hexadecimal number system um, is base 16. All right. So it utilizes a base 16, which we know that 16 is equivalent of 2 to the fourth. Now, this is important because we say here that hexadecimal numbers are 4 bits. All right, so once again, this is the idea of how do we store in computers. So we want to be able to store those numbers and how many possibilities there are. So 1, 2, 3, and 4. We have here 4 bits, and basically what is done is that all of the numbers are kept in terms of its data in this form. So it's a storing method. It's all about computer processing. This is the most widely used number system in computer programming. Or I want to say most, I'll put it in quotation marks, in computer programming. So when you hear about 60, so most of the applications that were used were using 16-bit. So what that means is that something has to be able to read in terms of to be able to process. So when you talked about a lot of the apps were initially 8-bit. All right, so they were in the basically being or sorry um, they were, well, I don't want to say. Um, I don't want to get into because I am not an expert in the concepts of those with the applications, but in its premise, everything comes down to the type of numbering system that is used. So when they were referring to how the applications are created, it's a form of efficiency and security, and so I know Apple, for example, changed that. It used to utilize, you could use this or this in terms of basically saying the numbering system and the coding that was within it. And then it had to be translated into its new form. So you had computer programmers that had to change their codings as such, or their application was going to be like left off of the App Store when it regards to like something like Apple. So it's all about computer programming. It's all about 16-bit, and of course we know the idea and the premise is using the numbers, um, but of course we have 16 to the 0, which is 1. We have 16 to the 1, which is 16. We have 16 squared, which is 256. 16 cubed, which is 4,096, and so forth. So each of the digits, when we talk about the digits here would be for 1, for 16, for 256, for 4,096, and for each of the numbers, and this is where it's going to get a little bit different, how many different values can go within each placement value? How many different values can go into it for, now remember, for decimal, it was, well, how many values, how many options you have for binary, how many options did you have for octal, how many options do you have for decimal, how many options do you have for hexadecimal? No, it's not 4. I think you went backwards. That's how many digits. So this is an example. This is an example of a 4-digit hexadecimal. You can have a 1-digit hexadecimal, but the idea is that in each of those digits, each digit can have how many options? The answer is 16 options. There's 16 possibilities for each one of them. But if we know our numbering system, it kind of gets you a little confused because, excuse me, with decimal you had 0 through 9, and so each digit can take on the values 0 through 9 and A through F. So this numbering system actually has letters in addition to the numbers, and you might have seen this in some instances and never knew what it was meant for, but that's what it is. So basically, 0 equals 0 to 9 equals 9. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. We only want to be able to have, we can only really have single digits for each one, or one thing to represent it, but because it goes up, we use the letters. So now this is widely used. So the numbers A through F actually represent the values of 10 through 15. So if I just gave you the number 0, if I just gave you the number, for example, D in decimal, or in hexadecimal, D in hexadecimal represents the number 13. So if I just had single digits, the letter D represents the number 13 in base 10. Okay, so that's of course if we're just using one. So when you have these numbers, and this one's going to be a little bit trickier because you have to basically make sure that you're looking at this, that A is 10, B 11, and so you have to convert these letters into their values 10, 11, 12, 13, 14, 15, and do the same things that we were doing. Okay, so let's do an example. We're going to convert the following hexadecimals, and this is all you're going to be doing for your homework, to their decimal form. Okay, and my first one, can someone give me a 2-digit hexadecimal? Someone give me something in 2 digits. And you can use the letters A through F. You can use numbers, or you can use the letters A through F. You want to just start off by giving me just 2 numbers? That'll be perfectly fine.
48.
48. So we want to turn 48 from hexadecimal, and we want to find its decimal form. Okay. Now, once again, same idea. We read right to left. All right. So the 8 will be to the power of 0, and 4 would be to the power of 1. So this is going to be the same thing as 4 times 16 to the 1 plus 4 or plus 8 times, or 16 to the 0. Now, that's what's going on. It's 16 to the 1, 16 to the 0. If you want to just rewrite out the numbers they are, this is the same thing as 4 times 16 plus 8 times 1. And remember, that last one is always just going to be like plus 8 in this case. So now we got to go into our calculator. We need to figure out what 4 times 16 is. So 4 times 16 is
64.
So this is 64 plus 8, which is
72.
72. So 48 or 48 in hexadecimal is the equivalent to the number 72. All right, let's do another 2-digit example, but this time I want you to give me letters and a number.
D64.
2 digits.
64.
No, I want a letter in there.
D64.
That's 3. We can do that. We can do that example later. I want 2 digits. Replace one of those numbers with a letter.
So I pick 2 letters.
Or 2 letters. Well, I want a letter and a number. Or a number and a letter. A single digit number.
Sing the number 8.
No, it has to have 2 digits overall. One of those digits has to be a letter. Thank you, Brian. Brian says 5C. See? 2 digits. And this is a 2-digit hexadecimal number. It has a number, and where we can use the numbers 0 through 9, A through F, and Brian said 5C, and we want to convert this into decimal. Now we got to remember that C is equivalent to 12. So this is, when we do this, this is going to be 5 times what?
Times 16.
5 times 16 plus
C times 6.
No, what is C? You gotta look at that. We gotta look at that. It's 12. So it's 12 times
16. Times 1.
Times 1. That always one. Last one is always just easily times 1. No matter what the number system we use, it's always just times 1 at the end. So Brian's already gave me the final answer, but just to show my work, 5 or TJ. That was TJ. Sorry. 5 times 16 is 80. So we get 80 plus 12, which gives me 92. So 5C is equivalent to 92. All right, let's go to 3 digits. So let's go to the one that Leon keeps trying to say. So he kept saying D64, right?
Yeah.
And we consider this to be 3 digits. So remember, and we want to convert this to decimal. So remember, this is 16 to the 0, 16 to the 1, and 16 squared. So in this case, we're not going to multiply the first number by 16. We'll multiply the first one by 256. Okay? So what is D in hexadecimal?
13.
13. So D becomes 13 times
16.
1, 16, 64. Or sorry, 256. 4,096. That's basically 4 digits. I think is the highest I go. I don't even think I go to 4 digits. I might though. So it's gonna be 13 times
256.
256. Okay, not times. If you accidentally do times 16 and then you go into the next one would have to be 1, and you would go, ooh, I gotta shift things over. Okay, so if you choose one, the last one should always end. It should always end as 16 and then 1. Okay, plus
6
times 16 plus
4 times 1.
Yeah, and you could just answer. Always the last one just plus 4. But I like to see this times 1 because it knows that I've done the last step well, and I know I always end with a times 1. And then hexadecimal times 1 times 16. So if you accidentally wrote 16 here, and then you would be like, oh, 16 here, you would know that something was wrong. Okay, it always goes down in one order. All right. And so, ooh, we got to go with calculator. What's 13 times 256? And you got to break out the calculator for that.
3,328.
Plus 6 times 16. I got 96. Plus 4. And like I said, if you wanted just to go directly from here to here, and you don't have to show me what each of these numbers are. So if you're just plugging these numbers in your calculator, 13 times 256 plus 6 times 16 plus 4, you can just do it in one fell swoop. After that, you just need to show me what you're multiplying by initially. I get 3,428. Are there any questions about how to do these? It's the same process. You've done this with binary. You've done this with octal. It's the same thing as the day ones. You're just, instead of multiplying by, the numbers you're multiplying in this case are powers of 16. So 1, 16, 256, 4,096, depending on how many digits there are. So of course, I'm not going to just give you one digit, because one digit is just the number. So in minimum, it's 2 digits. And typically in computer programming, hexadecimals are usually 2 digits long, because that's usually as much RAM or processing that we have. So we go, well, actually, yeah, so 16. So 16 times 16. Well, 256, just like I said. So usually we go like, there's a lot of storing methodologies that are used, but that's it. So you can have multiple letters. You can have all 3 be letters. You can have all 4 numbers be letters as well. Once again, any questions? All right, go forth to the rest of the class is asynchronous. You're doing this just like before. I gave you 8 problems. In your homework, use the rest of the 30 minutes of class time. Or sorry, not 30 minutes. You have a little bit less, 24 minutes to complete this assignment. And that's all I have for you.